Hi there, this is Math 116, section 4.2, and in the next two sections introduce the topic of linear programming, which sounds like something you should be doing on your computer and not in a math class, but we can in fact do this with math. And there's a nice little description on page 268 which says, we're often looking at problems that involve several variables, and we have lots of constraints on our variables. So you can imagine a manufacturing situation, and you have different things, and these two things have to be less than 80, and people can only work so many hours a day, and you only have so many shipments that can come in. So you have lots of variables and lots of constraints, and your goal is to optimize either profit or revenue based on these different constraints in your problem. So when we talk about linear programming, in your mind, think about problems. Linear, what they tend to be for this two sections is linear inequalities, and they call them constraints. Like, well, you know, your workers will only work 40 hours a week, that kind of thing. Linear inequalities or constraints, and we are trying to maximize or minimize certain things based on our variables. Maximizing or minimize. What would we maximize? Revenue, profit. What would we minimize? Cost. Something like that. So I'm going to just jump right in and take a look at question number 9. So the reality here is you just want to know how to work these problems. So here's a problem. We have, it says maximize f, it's our little function, which is going to be 30x plus 50y. What is x and y? We don't care. At least we don't know for this problem. In other problems, you will know what x and y are. Subject to, so you have the following constraints. X plus y must be less than or equal to 48. You have x plus, oops, that was x plus 2y. X plus y is less than or equal to 30. 2x plus y is less than or equal to 50, and all of these equations would come out of some problem having to do with the various variables, like the number of things you can produce and how many can be made in each factory, that kind of thing. But here's some examples. X plus 2y less than 40, x plus y less than 30, 2x plus y less than or equal to 50. So we're trying to maximize this subject to these constraints. So to work these problems, the first thing you want to do is focus on the constraints, and we're going to make a little map. Constraint. So this section, section 4.2, is all about graphing solutions, and in section 4.3 we're going to solve this with your favorite, not factoring, matrices. So for this section 4.2 we're looking at graphs. The first thing you want to do for each one of these constraints is write it like an equation. You're going to graph each line, sort of like we did in 4.1, to make a little boundary line. So I'm going to rewrite the first equation as y equals negative 1/2 x plus 24. I did a big step. I took the x on the other side and divided everything by 2. I'm going to write this equation as y equals negative x plus 30. And then I'm going to write this one as y equals negative 2x plus 50. So the reason I write them like this is they're a little bit easier to draw the lines. So I'm going to draw on a graph each one of these lines. So the way you do that is you find 2 points for every line. I show you. So the first one, you have y equals negative 1/2 x minus 24. Plus 24. Sorry, plus 24. So just pick, so for this line you get 2 points. I always like to pick x equals 0 for one of the points because that's easy to do. X equals 0, y equals 24. And then just look at this equation and you can pick whichever one you want. I think if x is maybe 4, that's kind of easy. Or x could be 10 or whatever. But let's let x equal 4. That way 4 would be negative 2, so that's like 22. It doesn't matter what points you use because any 2 points you can draw the line between them. The second one is y. This will be the first one. This is the second one. We have 3. I'll get to the greater than or equal to 0 ones in a second. The next one is equal to y equals negative x plus 30. That's the second equation. So we're going to get 2 points for this one. And again, I like x equals 0 because that's easy to figure out. Let x equal 0 there. Heck, I'm going to let x equal 10. So now Negative 10 plus 30, 20. It's easy to graph. Just think in your mind, what is going to be the easiest for me to graph? Make your life easy. When is your life easy? It's never easy. Okay. Third equation here, if we let x equal 0, y is 50, and I'm going to let x equal 5, because then 5 times negative 2 is 10, negative 10, so that's 40. So what you're going to do is then take each one of these, and you're going to draw a little graph on a piece of paper, like this, and you're going to go, okay, these kind of go from 0 to 5. See how that goes from 0 to 5 on the x-axis? And how this goes, it's like in the 40s and 20 to 40. So you're probably going to go 1, 2, 3, 4, 5, like that on this side. And then you're going to go like 5, 10, 15, 20, 25, 30, 35, or maybe 10, 20, 30, 40, 50, something like that. And then for each one of these, you're going to draw the line. 0, 24, 0, 24, like that. So you're going to draw 2 points, 4, 24, 4, 22, like that. And then you're going to draw a line between them till you have 3 lines on your graph. Okay? For the purposes of your homework, your graph can look like this. This is perfectly okay. And on a test, I will have a prettier graph for you to interpret, so you don't have to worry about precision graphing by hand. That's not what this class is about. So when you are done, you're going to end up with, what? Is that what your paper looks like? So I plugged in these lines. X plus 2y equals 48, x plus y equals 30, and 2x plus y equals 50. So in theory, your graph should look like some sort of slightly messier version of this. And similar to what we did in section 4.1, we are looking for the areas where everything overlaps. So I could imagine we want everything, I'm going to use my mouse, the mouse won't draw on it, less than this green line, less than the green line. We want everything less than the blue line and less than the red line. So we want to look for the region where everything overlaps. So hold on, I'm going to paste this. Actually, maybe I can just pull it up on my paint picture here. Let's get up a new paint picture. Hold on. I took this graph and I pasted them here into a nice paint picture. So you should have something that looks sort of like this. And what you're interested is finding the region where everything overlaps. So imagine if you said, I want the area that's under the green line and under the blue line, right? And under the red line, I should have had these better color coded like that. This one goes out farther. There's 3 lines, and we also want x bigger than 0, so we want everything on this side, and y bigger than 0, everything on this side. So imagine if each one of these lines, if it was like a piece of gel colored paper that you would put over a light, and you want where they all overlap. I guess it could be fabric or anything you want. So what we're going to look for is what they call the corners. Corners. Yep. So if you imagine where the overlapping section is, it's here, right? Right there is one corner. Here, that's where they all overlap. Here. I was thinking here, but no, the blue line goes below it. So here, and then here, and then there. What? Do you see the corners? If you laid each one of these out like fabric, where would they all overlap? Where you have 3 layers of fabric. And your corners are 1, 2, 3, 4, and sort of 5 corners. So first thing you want to do is identify the corners. And you're thinking, well, if I have this graph, it's really easy to see that this corner has the dot 1218 because I just wrote it on the graph. But how would you find this 1218 point if you didn't have it beautifully on your graph already? Well, you would take these equations and let them equal to each other and find where they're equal. So you would say, well, I know x plus y, that's 30, so that means y equals 30 minus x. So I want that line, see, the blue line, want that to be equal to, you say 2 equal to the red line, x plus 2, and then you let that y value go in there. 30 minus x, like that, and you solve for x. You should get 12. By the way, that should be equal to 48. Can't 48 on the edges. So you can figure out which 2 lines are intersecting and then use these, the things that we did in, I think it was chapter 1, about solving for x and y, where the two solutions of the equations. Do the same thing for there, 20, and that's just 25, 0, because that's the one line. On your test, I'm going to give you a nice picture like this, so you don't have to worry so much about finding these intersection points. But now that we have the corners, we have 1, 2, 3, 4, 5 corners down here. I'm going to include this one even though it's not going to matter. What do you do with the corners? You're not quite done yet once you have corners. So here's what you do. You make yourself a nice little chart that looks like this. Corners, right? The corners. 0 and 24, that was one corner, right? 12, 18, that's another corner. This is fun, right? This almost makes the next section. 20, 10 is the other corner right there. See? I'm writing these down. 20, 10. This corner here is 25, 0. 25, 0. And I'm going to put 0, 0 on there because technically that's a corner right here from the bottom. And I think if I used the fill tool, you wouldn't be able to, it would fill in too much. It's not very accurate. But this right here, like this is our region that where all of the constraints are true. So we found the region where everything's true, but we still haven't actually solved the problem, which is to maximize this function. Remember this function? We forgot about this one, right? Well, he's back. We didn't use him till the very end. Once you have your corners, you come back and get your function, which is f equals 30x plus 50y. It's over here. F equals 30x plus 50y, and then you plug in. This is x, and this is y, for each one to figure out what f is. So for this one, f is 30, it's 50y. 30 times 0 plus 50 times 24, it's 1200. For this one, you plug in 12 and 18, and you get 1260, right? This is what f is. Whatever you're trying to maximize at the point 2010, your f is going to be equal to 1100, and I'm just plugging x as 20 and y as 10 in there. When f is 25 and 0, you get 750, and at 0, 0, you get 0, so that's probably why they don't often include this one. So now, because the question said maximize, did the question say maximize? You've forgotten. Maximize. The question says maximize, so we look at all of those and we just find the biggest one. Okay, what's bigger? 1200, 1260, 1100, 750? I believe we go with 1260. So this is your final answer. A maximum of f is 1260, so if that was your profit or something, you're getting 1260 at the point 12 and 18. So if I give you a picture like this, this whole problem should go much faster because then you only are looking for the corners. And if I gave you the points, that should be faster. So again, quick steps. Take these three equations, write them into, so take your constraint equations, write them such that you can graph them. So find some points for each constraint and draw the boundary line. Then on your picture, look for where all the boundary lines overlap and draw little dots on the overlapping corners. Find your corners. Find your corners. I always feel like saying corner like my friend Heather, who has a Boston accent. And then once you have your corners, you plug them into the function that was given at the beginning, and you look for a maximum. If the problem asked you to minimize it, you're going to find the smallest one, which will probably be 0, but you probably want it minimized bigger than 0. So try these problems. They're a little tricky. Don't get too hung up on the graphing. And then when we get to section 4.3, you'll say, maybe I like the graphing better.